Okay. So do you think about it? So how much relational was actually this task? Where are we doing so far relational learning? Yes, no, or at some extent, yes? Has anyone an idea? Even if you didn't think about that during the coffee break, maybe you can think about that now. So clearly it depends what we mean with this question. We are using this elegant logic representation, so in a sense, we are using certainly a relational learning framework. But what I mean is that we are not really exploiting nothing of the structure. We are just using attributes of the nodes and only of the nodes to predict the link between the nodes. Okay, so there is a link only if I am green and he is green, or a red and the blue, but it's just my property and his property, and there is no sense in using also other properties of other examples of other nodes. So in this sense is not relational. Okay, I can build a supervector machine or a neural network or a decision tree where each example is a pair of nodes, 6 bits, 3 bits to encode the color of the first node, 3 bits to encode the color of the second node, and you have a 1-0 class. Okay? Any propositional classifier would do the same. No need to exploit strange statistical relational learning stuff. And that's a very crucial point because, well, actually, there is one thing which was relational, which was the symmetry. Okay? I wanted that I put an infinite weight there. If xy is true, then also yx has to be true. That was really the only, let's say, predicate which transferred information, if you want. But, I mean, that could be also easily replicated in the propositional setting, because if you know that in advance, and if that is known by the expert, you just use in your classifier one of the two pairs, not the symmetrical ones, and you are done. Okay? That's a crucial point because if at some point during your research you will write a paper where you will successfully use a statistical relational learning framework, I strongly recommend, because I think that reviewers otherwise would ask for that you compare against a non-relational system. Okay, so a propositional class. So why are you using this stuff, which, I mean, 40 seconds to run a training on 10 nodes? Of course, it's elegant. You can write rules in logic, which is wonderful. It has some interpretability because you have the weights, which are a little tricky, but they are interpretable. But if you use decision trees, they are interpretable as well. Or, I mean, a lot of other stuff is. So if you really think that it is worth using statistical relational learning, you should show that in your experiments, or in the theory, but also in the experiments, I think, because otherwise, why there is no way in using complex things if simpler things are doing the same in a much more efficient way. Oops. Okay, so if we go back here, okay, there is also another possibility, version 2 of the MLN, which encodes differently the colors. So you do not have 3 predicates for colors, you have 1 predicate, which is color, and is binary, because it says that color of a node has certain value, okay? And this is useful to show that in this way, there is a shortcut in alchemy to write just a single rule instead of writing down 1 rule for each possible pair of colors, okay? So here I'm writing that color of node X is C1 and color of node Y is C2, implies that there is a link XY, and I use the plus sign before these 2 variables, which in alchemy syntax means, okay, now this rule is transformed in a list of rules where you substitute every possible constant to this variable. And if there is more than 1, you do the Cartesian product. So all the possible combinations of colors, okay? So maybe, I mean, we are just example number 1, so I will not show it in the command line, but believe me that if you run the learn weights, yeah? No, because, so, okay, so let's have a look at it. So, version 2. Now, this is the MLN. You have 2 predicates and just 2 roots here, okay? And the database is like this, okay? But remember, to answer your question, that in Markov logic, you have a weight attached in general to each first order logic clause, not grounded clause, okay? So here in the previous version, you have a weight to each attached to each possible first order clause, okay? For a combination of constants, so in this case, it will learn different weight when color C1 is red and C2 is red, C1 is red and C2 is green, red and blue, and all the 9 combinations. Okay? But this is an exception in which you have a rule which depends on a constant and a different weight for each ground. Okay? Otherwise, the weight is to each first order clause in Markov logic. Remember that. There is also, I think, a 3rd version. Yeah, it's in the slides also or not. Let me see. Well, no, then in the slides, then you have ProBlock. But I want to tell you something more also here. I made also a version 3 where, to make you understand a possible problem, there is also another predicate which is not black, okay? Which trivially is true for all the nodes here, all the red, green, and blue are also not black, okay? Now, if in addition to, for example, these rules here, you also add a rule where you also say that red X and not black X, which of course is true for all the example for which just red is true, because every red is also not black, okay? So all the groundings that satisfy these also satisfy these, trivially. But only because of the fact that you have added this clause with its weight contributes, okay, to the overall attempt to satisfy the maximum probability assignment. And so you are, in a sense, artificially adding evidence, okay, also to things that were already given here. Okay, this maybe can be not that, I mean, obvious, or maybe it's a little counterintuitive, but what I mean is that Markov logic allows you to write down rules very generally, okay, but you have to be, and sometimes it's useful to have rules for which you add basically additional information with respect to previous rules, as here. But sometimes it's not, because in this word here, in this MLN here, with the same identical data as before, okay, now the red and blue pairs are more probable for the inference, because there are more rules which have to be true, okay, for that pairs. More rules that are satisfied if a red-blue pair is true. So, which means more groundings, which means a larger n of x in the formula, which computes the p of a word, the probability of a word. Okay? So that's just to say, be careful, because the weights sum up in Markov logic, sum up, and so you can easily artificiously introduce maybe things that not necessarily would like to. You have to think upon it, and you have to, I mean, build your models, try them, and observe what happens. Okay. So let's move to Problog. If I want to do the same with Problog, what can I do? Okay, I have again to write a model file and a data file, okay, similar to, in this sense, to Markov logic. And in the model file, you write again the rules, okay, which again have the opposite syntax of having variables in uppercase. So here with this syntax t underscore, you are saying that you want to learn this weight, this parameter, okay? For which rule? For rule red, red, green, green, blue, blue, red, blue, and all the possible pairs. And maybe you can also add a rule with a fixed weight, which is the symmetry. And you put here maybe what is, basically it's the background knowledge, what is always true, okay, which are your facts about the colors, okay? In the data file, you have the predicates that you want to infer, okay? So the query predicates for which you have to state what is true and what is false, okay? That's very similar to the DB file in this sense for MLN. Okay, here you can both try the command line or the browser. Let's see what happens on the browser, for example. Blog. Okay, try inference and learning. So I have to, let me see. That's more, if I here select learning, you see that he wants the model and the examples. Okay. So this is the model. Okay. And the evidence, the other file. Oh, that's too much. Can we open with the text editor? Yes. No. Okay. Inconsistent evidence detected. I wrote something wrong. Yeah, it's the new line. It's the new line. Again. No, well, come on. No, but this is if you have different interpretations. I'm pretty sure it will. Let me try from the command line. It's Problog. You have to. You can. I'll show you that you can do either inference or export by then. You can do several things, and one is LFI, okay, which is learn parameters from data, which has its own help, okay. So if you do LFI and then the model and then the data, let me see, let's see if it also, yeah, here it works. So, well, I don't know. I was pretty sure it worked. So we will check again the browser in a minute. It's not so interpretable here, but it's in the, so we can run it in, I think, in a verbose way. Let's see. Yeah, again, it's not that much interpretable. We can also have the, I'll be a little slower now. So the command line interface, you have to tell Problog that you want to perform learning from interpretation. The first input file is the model, the second is the data, and you also can have an output file, which is the output. Maybe in this way it's a little more interpretable. Let's see. No, it's the same. Minus big O. Let's see. Anyway, it's in the order that you specify the rules. So I don't remember. Something changed. Okay. Right. If you specify, sorry, it was not minus lowercase o minus uppercase o. Okay. Then the model, the file that is written is really interpretable, okay? And you can see there that it is assigning probability 0.42 to the fact that it's green, green, 0 to everything else, and here there is a little surprise, but so happens that the probability of red, blue, and blue, red is not the same, okay? Even though you have the symmetry here, okay? Now you see that it's different from Markov logic, that you have not a real valued weight, but you have a probability. And of course, also for inference, you have all the advantages of having the elegant probabilistic framework with Problog, and with the CP-link, we'll see in a minute, which you do not have for Markov logic, okay? Let's have a look also at, I think I can close this. I have no idea actually why this did not work on the, because it's the same. I don't know. Let's have a look at CP-link with, okay. Fabrizio, if you spot something that could have been done better, please tell me. So you initialize, you have to initialize, you need a little preamble here. You tell CP-link that you are going to use the slipcover module, which is the one which performs learning, okay? With this command here, you are saying that you basically instantiate the module, okay? You load module. And in here, for example, you can set a lot of parameters of the algorithm. You have a full list of it on the manual. There is quite some stuff that you can play with. Here I just changed the verbosity because it's nice to see the outcome. Then you have a section where you specify the input theory, okay? So in the input theory, you have basically a list of the rules. Again, it's very similar in the sense to the Problog syntax, but here a weight which is not important, its value, because it's not used for initializing the network. It just means that you want a weight there, and so slipcover is going to learn the weight. It's just important that you have a weight here, a probability. Also, Fabrizio, in one recent release, gave the possibility to also have fixed parameters that you do not want to learn, because you want to have them given by some knowledge, okay? And it is if you specify P of a number. And you also can set an initialization parameter, which is T of number. Then you have to specify if there is a background knowledge, and most importantly, what is called a language bias, okay? Which you have seen also this morning. And it is in this way. You have to specify what is your output and what is your input. Basically, it's what in Markov logic, it's a query or the evidence. And same as with Markov logic, what is output, what is to be predicted is open word, so it's not CW, not closed word as red, green, and blue, okay? And the number here says the arity of the predicate, okay? So this is binary output, the link predicate is binary, and red, green, and blue are unary, okay? So this is the number. And then you have the modes and the determinations, which you need to specify. So the modes, mode H and mode B, stays for mode for the head, mode for the body. So in the head, you have only the link predicate in the head of your clauses. And in the body, you have the colors, okay? And the determination means that you have clauses where you can have link in the head and red in the body, link in the head and green in the body, link in the head and blue in the body, basically. That's the meaning. Then you can specify that there is a fault upon which you want to train. Okay, and this can be a list of several words. Okay, several macro examples, as Fabrizio called them this morning. Okay, here I just have one single macro example. Okay, the training set, which contains everything that we have seen in the MLN and ProBlog okay, models. So it's the facts. This also can be in the background knowledge if you want. In this case, it's the same. And you have some true facts and some false facts, which are the negation. You know that this predicate is true. You know that the negation of this predicate is true. So it's false. Okay. So, okay, we stop a little here. Let me, where are we? Okay. Let's take the thing. Right online. So here, create. This is the CPLint EU website. Here you have a lot of examples that you can load and try. Or you can create a program, and here you have some possibilities where basically the interface loads for you already what is needed. For example, if you know that you want to do learning, you can say, okay, I want to do a program with a slipcover. Okay, you want to create a program, and it already loads you the different parts that are needed. Okay, it says you the instantiation and so on, the settings, the input theory, background knowledge section, and so on. Okay, so you can now, in this case, I copy and paste, so I don't need it, but it's very useful. And basically, what I'm doing here is to run the induce par query, which is induce parameters. We'll see later that just induce is inducing the rules, so learning also the structure, while induce par is inducing just the parameters. And if you run this, okay, it's finished. You can, this is the initial theory. It gives you some information about the emblem algorithm here, and at the end, here is the final theory, which says that these are the only non-zero rules. Okay, and so green is true with 0.67. Okay, and red blue and blue red have 0.3. Okay. That's basically the way in which you do the same thing in the three languages, frameworks. So we have already talked about this. We are not actually performing real relational learning, but one more point on this very stupid example. What are the main advantages and disadvantages of these three different frameworks? You cannot really tell whether one is the best. It depends on your problem. There are some things that you can, from which you can get an intuition already from this simple example. So I would say that writing down and having an example run on Markov logic is maybe faster. Okay, because you just have to write down just the predicates and rules, just the DB file. It's fast. But you will see that it's also fast to get wrong things. Okay, so to write the model in a way that it makes things explode, or I mean, the rules that you write are not exactly what you were meaning. Okay, while in the in both Problog and CP-Link, which maybe require a little bit more experience to perform some of the experiments, but you have all the probabilistic logic programming, the Prolog behind, and this makes a difference, okay, in terms of interpretation and in terms also of clarity of the explanation, I would say. So, I mean, there are pros and cons of all. I think I'm quite fair in saying this. Okay, let's move to another example. Now, yeah, we have 1 hour. I would like to have, again, half an hour in which I talk about these examples and half an hour in which maybe you try to do something and we discuss the exercises. So let's see. So the second example, again, is something that has been mentioned in several lectures, also by Fabrizio this morning, but also yesterday and on Monday, hypertext classification. So this is one way to model hypertext classification with MLNs. So you have pages, web pages, and you have links between pages, which this time are given, are observed. The links are something that is in the evidence. And what you want to predict is the topic of the page, okay? So the topic depends clearly on the words in a page, okay? But also the links help you in disambiguating whether same words that can appear in different topics, maybe because a page is is linked to sport pages, is likely to be also sport page, okay? Now, this is one way to model the problem, Markov logic, with three predicates. So has word, so a page has word, link between pages, and topic, page, topic, okay? And here are 2 rules here. The first rule says that if there is word W in page P, then it's likely that topic of P is T, okay? Again, there is a shortcut here with the plus, which transforms. I'm sorry that I continuously switch from the presentation to the terminal, but I think that there's no other way. So let's move to example 2, MLN. Okay, so see the DB. So you can say that well, page P1 has the word soccer and goal, and page 2, England defeat Colombia, soccer, goal, etc., etc. Okay. So if you run, okay, let's run also this one. If you perform learn weights, you give in input the MLN. You give as training data the DB file, and you have to specify the output file out. And the one I always forget is that you have to specify the non-evidence, okay, which is, in our case, the query is topic, okay? Now let's read it. For those of you who are not familiar with Unix or Mac, this is going to redirect the standard output to a file, okay? So instead of seeing all the terminal with the stuff, everything is written to this file, okay? Okay, it's done. So if we open now the output MLN, it has prepared a ground instantiation for the rule has word topic, okay? So there is a good weight 1.228 that if there is word goal in P, then topic is sport, okay? And similarly, there is a negative weight if there is coffee, okay? All the possible combination in this example, I have 3 topics: food, sport, and politics. Yes. And I have, I don't know, something like 10 or 10 words, maybe. So let's go a little back to the original MLM. Then we go back to what has been learned. But what I want to say is that this rule here, if you ignore the second, okay, the first rule is exactly what? Has any of you an idea of what the model with just the first rule is more or less replicating? More or less. What, sorry? Naive Bayes, you say? What? Yeah, more or less. I mean, it's or logistic regression. I mean, it's basically you have features which are words. So you can imagine that you have something similar to a vector of as long as the vocabulary, okay, with the one where the word occurs and 0 otherwise, what is called a bag of words. Have you ever heard of bag of words? Almost all of you, I think. So you have the feature vector, which is your vocabulary, and you have everywhere 0, but you have a 1 in the feature vector if the word appears in the page. Okay? No matter of the order. No matter of the order. This is why it's called a bag of words. It's not a sequence, doesn't take into account the sequence. A scrambled page has the same representation, okay? And basically you learn a different weight for each possible word topic pair, okay? And so you have a weight for each feature, basically, which is every word. So it's more or less a logistic regression. By the way, here, for how I wrote the model, topics are not mutually exclusive. Okay? There is nothing in the model which says that topics are mutually exclusive. I would need to add something to the model if I would like to do that. Possible variants of discussing this kind of models are infinite, so I mean, I keep describing, but if you have questions, please ask. The second rule is different because you have the query predicate both here and there. So what does this rule say? It says that if page P is of topic T and there's a link from P to Q, then also Q is of topic T. So this really is a rule which allows to, make the information pass from one node to another, okay, in the network. Because if this rule results to be true, so high weight, okay, the inference algorithm, for example, the map inference algorithm, will prefer solutions where linked pages are of the same topic, both sports, both food, rather than one sport and one food. Okay, if possible. Clearly, it's not always true. It's soft logic, so soft constraints, but that's how it goes. So let's see which kind of weight we have here. Yeah, 0.68. So it's positive because I can show you. You can also check in the DB file that I built the network in this way. So there is a link really between, mostly between pages with the same topic. Okay. So if we want to do the same for Problog, you can do the same, also using the trick of specifying something that is similar to the plus sign for alchemy. So you can specify that you have topic PT if there is link PQ and topic PQT, and this is one rule, let's say the relational rule. And then you have also the sort of bag of words rule, which is just one rule, as in the case with the plus sign. And here, with this syntax, you say exactly like in alchemy that for each possible combination of constants of W and T, you are also going to learn a different rule. Okay? Exactly the same as with the plus for alchemy. Okay? So you will have a different weight for coffee food, coffee sport, and soccer sport, soccer food, and so on. Exactly the same. Now, in the zip file, you also find the same model also for CP-lint, where, by the way, Fabrizio has been so kind to add the same feature also for CP-lint, but in the example I prepared, instead I have not been as kind as you have been. So I listed all the possible pairs of word and topic, but now you can do exactly the same with CP-lint. So now that's a good question, I think. Now, if this model does exploit relational information, yes. What if we want to use, now, suppose that you are writing a paper where you used your fantastic new statistical relational AI model to perform hyperlink classification, okay? And you want to convince the reviewer that your model is great, and of course you compare against maybe Markov logic, maybe against Problog, or against LPAD with CP-lint. And the point is, I also have to convince that relational information is important. So which kind of experiment can you add? Can we model exactly the same problem with standard machine learning classifiers? Yes, no, maybe. I think not exactly, so not completely, but for sure you can do the bag of words with any of these classifiers here, just bag of words. And you can, maybe that would be nice to see that, as an exercise for you, to see that if you remove this rule here, if you remove this rule here, or Markov logic, if you remove this rule here, so if you remove the relational rule, both Markov logic and Problog with just this rule should not be that different with respect to, I don't know, an SVM or another propositional classifier with bag of words. Of course, there will be some difference because every algorithm has its own optimization, but should be more or less the same. It's elegant to see it in this formalism, but the expressivity is the same. What you cannot do is to do collective classification. One thing that you can do maybe with a propositional classifier is that you do a first classification, okay? And then you use, so I'm not talking about now statistical relational stuff with SVM, say, or with a neural network. You classify the pages and you get a result. Now you take this information as feature for a second round classification. Okay, that's a little dirty, it's ugly, it's horrible. That's the way that you should do that with statistical relational AI. But maybe you can observe some differences. It would be interesting as an exercise, okay? To see that if you provide to the propositional classifier this additional information, things may change. But anyhow, collective classification is not something you can do with propositional classifiers. Okay, let's move a little bit to next example, number 3, which is here just about representation, okay? Here I want to discuss a problem that you have with Markov logic, basically. Now, in proteins, there is an interesting classic problem which is predicting the secondary structure, okay? So you know that a protein is a string of characters from a computer science point of view, is a sequence of symbols, 20 possible amino acids in your alphabet. And this protein folds, so its three-dimensional structure, it's known from biology that it only depends from the primary structure, which is the sequence, okay? So to predict how it folds is, I mean, holy grail problem in biology. And predicting what is called the secondary structure is an intermediate problem towards this. It means that you want to predict the sum of the three-dimensional structure of the protein. For example, you want to say whether some of the amino acids are arranged according to an helix, or instead to a flat, what is called a beta sheet. They are three-dimensional structures, okay? So it happens that typically, if this is written in logic, if in sequence S, position P1, sorry, is of class C, so for example, is an helix, is within an helix, then also the successor of P1 is also an helix. Typically, it's like that. So this is a rule that you would like to write in MLN or in Problog or in LPads. What's the problem in Markov logic is that if you model the problem like this, so you write a predicate which is residue in sequence S in position P is this amino acid, so in this way, the Markov logic engine with alchemy will build a lot of spurious, unwanted predicates. I have an example later, and then I go back. So suppose that you build a database in this way. You see here that you have residue in sequence S1 at position 1 is a C. Then residue in S1 in position 2 is another letter. And the first sequence has 72 residues. So the last one, residue 72 in sequence S1 is an A. That's the end of the first sequence. And then you have second sequence. Second sequence S2, the first residue is an R, and the 66th is an S. Or you have 66 of them. Now, if you put everything here in a single DB file, okay, and you perform learning or even inference, the same. But anyhow, if you, for example, perform learning, Alchemy will also expect, and in this sense, it will build, if it doesn't found them, also the predicate, for example, S272. Okay? Because the definition of the predicate is like that, okay, of residue, and the query predicate, which is secondary structure, has the same, okay, 3 arity, okay, and so it will build all the possible crossing groundings for all possible values of type sequence against all possible values of types position against all possible values of times class. Okay, so basically what I mean is that Alchemy sees S1, S2, S, blah, 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 as possible sequences. It observes P1, P2, P, blah, 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 upon P, I don't know, the maximum length sequence, maybe it's 120, I don't know, as possible positions. So it will build all the groundings up to the maximum length of all the sequences in the DB file, okay? Which is something that you do not want, because some of these are clearly unwanted predicates. These are spurious, that do not make sense, because sequence S1 has 72 and sequence S2 has 66. Position 80 doesn't exist for sequence number 2, okay? But it will, in any case, build all of them. So there is a solution to this, but you have to be careful, because you have to understand that you have to use this solution. The solution is that you have to use the option which is called multiple databases, okay? So you have to put every protein in a single different DB file, okay? 1 DB file for each protein, 1 DB file for each. In Problog or in LPADS, in Cplint would be interpretation, okay? Macro interpretation, if you want, macro example. 1 protein is a little small word there, and it is independent to all the other proteins. So you train, basically, if you want to think as it's a mini batch where 1 protein is a different mini batch, if you want, okay? This is something that only affects Markov logic, because with Problog, with LPAD, Cplint, you just have to, you perform basically learning from interpretation. So what you have seen here, for example, here, this is 1 interpretation. So it's by default you have to write them here, okay? You cannot do another way. Okay, I'll move on. I'll be a little quick. Maybe there is no time to do everything with all the different models. So let's see. Also, this one, this is interesting because I was also performing. So I think I will do this. Maybe not with MLN, which also is interesting for some reason. Okay, let's try to do everything. Maybe we skip example 5. Here you want to do, for example, suppose information retrieval, okay? So you have, again, pages where you have, same as before, page has a word and there is a link between pages. And also you have a query, so a word appears in a query, okay? And you have the target predicate is to say whether a page is relevant or not. So you can, again, this is very similar in the formulation to the hyperlink classification. So you have word W in page P and W appears in the query, then the page is relevant. But it's also relevant if it's linked to another relevant page, maybe. Okay, this is with Markov logic. Before doing this, if there is time, let's see with Problog, it's the same. So you specify maybe a prior for relevant predicate, and you specify that the same two rules that you have for MLN. And you have your database of ground facts, and you have the query predicates in your data file. But what is interesting, and I want to show that both for ProbFoil and also for CP-Lint, is that you can perform structural learning. And this is something that actually doesn't work well for Markov logic. Let's try. So we are example 4. Okay. So here you have, again, the same files, which are the Markov logic network, the database. Then you have also a test if you want to perform inference. You have the empty MLN here with only the predicates, okay? And this is what you need if you want to perform structural learning, okay? You're just saying which are the predicates. So you perform learn structure. Now, I'm not sure of the parameters. So it's minus I, same as before. Okay, it's the same as for weight learning. So minus I MLN, minus T dB, and minus O MLN. Empty, yeah. Sorry, thank you. Empty model. And what is not evidence is relevant. So, if you observe this, you have to translate to understand a little better what this rule means. So, it's negative, the fact that you have a link. Let's try to write it in this way. So, I'll try to rewrite it here. See if I get it right. Should be like this. Get it right. So it's negative that if X is not relevant and XY are not linked, then this is not relevant. It's not so clear, the clause. And it's not, Yeah. What, sorry, Fabrizio?
You can write with this junction in the end. You say link A1.
Link?
A1, A2, or relevant A1 if relevant A2.
And
or
you can write it like this, and relevant y implies relevant x. Okay, but it's the goal here is to say that it's not so immediate to understand. In particular, this is what is written here. What's the problem with structural learning here? Is that you end up with this model where there is this rule which has a negative weight, so its negation is true, but it's not so interpretable. I mean, that's my whole point. Huh? You have the sensation, you have the feeling that he captured something, because there are the right predicates, but you cannot be sure that he got the way that you intended to, okay? So it's negative the fact that if there is not a link, basically you should write with a positive weight the negation of this, negation of the whole rule. Okay, you should apply the Morgan to this, okay, which becomes link xy, or to the disjunction. You're right. See, it takes time. So let's write it. So it's I like this, which is the same as before. Okay. But with a positive weight. Well, let me see if I got it right or not. Not. Or relevant, right? This is negated. Okay? So again, the Morgan, so not link. So I mean, it's not so easy. And relevant which is again not so intuitive. Okay, so basically that's my whole point here, was to state that structural learning with Markov logic, with the default algorithm of alchemy, is not so interpretable as probfoil and cplint are. Okay, if you try the same, for example, with probfoil, okay, I don't know if I have the in the slides the result. No. Try then, yeah, it's already 5.5. Try, for example, probfoil. In probfoil, you have to specify a setting file where you specify the modes, okay, and you have the modes that say that you have the predicates in query that can appear as input or output variable or constant with C in the clause that you want to learn, and the same for has word and also hyperlink. These are what you link or hide. In this case, I don't know why I call it hyperlink instead of link, but it's the same. And then you have type definition, which also contain relevant, and the target is relevant. Okay. Now, and the data file that you need to pass to probe file contains all the ground truth facts, okay? And you learn with probe file in this way. Oh, I think we installed that. We didn't? That's a pity. I have it on my laptop, but not. So we can try. Cannot try that. Can try with cplint. Let's try it on the learning with cplint. So let's open the browser here. Let's remove all this stuff. Let's remove these. And let's copy cplint, the structure file, contains what you need for perform structural learning. Okay, so again, it's with slip cover. Let's copy it on the browser and then we discuss it. Okay, so you have basically to load the library slipcover, for example, you set verbosity, and in this case, I also set this parameter, which is how many clauses you use as initial mega examples, which by default is 1, and here I loaded as 3. For example, I am using the fact that in my background knowledge, the query is apartment rent in Boston. Okay, and then I have, sorry, yeah. The output in the language bias is relevant, the output predicate, and the input close word are hasword, hyperlink, and in query. Okay, and you have the determinations, same as for learning, parameter learning, and then you have specified the modes. And here, briefly, want to put an accent to the fact that you need the sharp symbol for words because you would like that constants to appear in the clauses. So you do not want to learn a clause where a generic word appears. You would like to know to learn a rule where a particular word appears, so a constant. Okay, that's why you need the sharp here. Okay. So in this case, if you want to run structured learning, you have to call induce, non-induce par, and the fold is called train, so it should work. Oh. Take some time, maybe I have many modes, but let's see whether it arrives to something. You know, also writing, also verbosity makes it slower, clearly, because takes a while. You can probably, otherwise we remove some of the modes. Look at faster yesterday.
Many examples do you have?
I have, yeah, not that many, there are 6 pages, few hyper, but maybe it's the fact also I use the initial closest per megagram 3. I can make it 1. I remove this, and I can also remove one of the modes maybe. For example, if I remove the hyperlinks, yeah, it's nice to see the output. Let's see. Otherwise, I run it locally. Tough problem. Okay, let's say we leave it here. We'll see later what happens. And very briefly, I mean, statistical relational learning are tough problems in general, so no surprise here. Huh? If you write quickly models, you quickly can end up with very too complex stuff. That's true. So I will skip example 5, which is a recommendation. Basically, we already saw that for MLNs. These remarks on complexity are useful because these framework, the fact that they are very expensive, may them also quite memory intensive, also time consuming. So it's very likely that the first models that you write are not the most, efficient. They are most likely very expressive, but not very efficient. So there's some trial and error that you have to perform there. And it's very likely that you will need to reduce the expressivity of your model. Before going to the exercises for the last 15 minutes, which are the open challenges, already said, we need a more efficient inference algorithms to scale up with the large data set. We need better structural learning algorithms, which is by far the most difficult task. And one thing that I want to say is about continuous variables, continuous features, because everything that we have seen so far works nicely, almost, but everything is in the discrete domain, okay? Of course, it's logic. You have seen, Fabrizio has shown this morning, and also Luke yesterday, examples where you have continuous variables that you can use during inference. You can do that with Problog, with CP-Lint, with LPads. You cannot do that with Markov logic, okay? But in general, this is a key problem because almost any machine learning problem has to do with continuous variables, continuous features, because if you work with natural language processing and you need embeddings or you need, biological features coming from experiments, real valued numbers are there. We should exploit them. So there is a number of different approaches that try to exploit continuous features. Speaking only of those that I described, it's too late to go into this, but hybrid MLNs have been proposed to exploit, at some extent, very limited extent, I have to say, some predicate that is continuous valued, real valued. So for example, in order to write something like, there is some evidence that x is smaller than 2.3, then blah, blah, blah. Or product between the fact that some evidence is equal to 1.2, then blah, blah, blah. Okay, there are numerical expressions, but there's a couple of papers on that, but I think this direction was abandoned. okay? Then you have one thing on which I worked, which is ground-specific Markov logic networks, which in a sense is, I think, quite close to what Luke presented about deep Problog, in the sense that we plugged neural networks within Markov logic, making neural networks learn the weights of the rules. And so these neural networks could use any kind of features, including continuous features. Okay, if you are interested in these, I will send you references to our paper. There is also an implementation, which is a plugin of Alchemy. I have to say it's not so easy to use it, to be honest, because it was built on a previous version of Alchemy. It's not the current one. So, I mean, it's possible. I would really like to rewrite everything in now that in 2009 there was no TensorFlow. And so, yeah. The problem that I have had was exactly in bioinformatics to predict the links between amino acids. And so, yeah. Apply the theory to different data, because the input goes not in input to logic, but goes in input to the neural network, the continuous valued features. It's similar to deep Problog in this sense. Yeah, you have the formula here. There is a special in the syntax. I introduced this $, which means, okay, here do not use the grounding here, but actually put this in input to a neural network. It's a pointer, sort of a pointer to. Yeah. If you are interested, please let me know. That's the reason why I was particularly, interested. I think this is really the direction in which we should move to integrate this statistical relational AI with deep networks. So deep Problog is an alternative. Also, what Fabrizio presented this morning is a very interesting perspective for CP-Lint. And yeah, we have seen that continuous variables are usable in inference. Okay, there is actually not just the frameworks that I presented here, but plenty of other things from several groups. You will hear Arthur Davila Garcet's, okay, I think tomorrow afternoon or on Friday, I don't remember, is giving a lecture here at the school, and we'll talk about the field of neural symbolic learning, okay? So that's going to be very interesting, and I believe it will also make some interesting references to these applications. And actually, if you are interested in it, a seminal paper that I would recommend to read is this old paper of 1994, Knowledge-Based Artificial Neural Networks. It contains a lot of very pioneering ideas on this. How to use rules in neural networks or neural networks jointly with rules. It's very interesting. If you want to play with your frameworks and your models and do experiments, here is a list of sites that contain smaller and larger data sets, okay? In particular, the Stanford ones are very huge data sets, okay? While on the website of CP-Lint and also in Alchemy, there are the tutorials. So, I encourage you to follow them and play with the toy problems there. Then I have the Spartan exercises. Maybe, since there is shorter time than I expected, but in any case, I hope it was interesting. We can, the figure is not fantastic, but let's talk about this one, argumentation mining, because it's a field in which I'm working recently. So I think it's it has a lot of things that could be useful from the point of view of relational learning. So suppose that you have a piece of text. This is, you probably cannot read well, but it's a piece of a Wikipedia page, okay? And you want to extract the arguments from there, where an argument is, as I told you, a statement about something that you want to say, and it could be supported or not by some evidence, okay? So for example, this is the web page of Wikipedia about immigration, okay, which says, while these on the far right think that immigration threatens rational identity, as well as blah, blah, blah. So this immigration threatens rational identity is a claim. You can agree or not, of course, doesn't matter. And there is maybe somewhere in the text something that supports this claim, or maybe there is a claim which states the opposite. So the freedom of movement, both within and between countries, is a basic human right. For example, this, of course, is a claim in contrast with the previous one. So argumentation mining wants to extract the argumentation graphs given the text. Is a very tough task, very difficult, okay? Because it has to do with natural language processing, it has to do with reasoning, and so on. So suppose that you are given, what is the standard pipeline? Is that you are given text, you first detect which are the interesting sentences, and you then detect, you cut basically the boundaries of the claims or the premises that you want to highlight, and this is called detecting the components. So basically the nodes of the graph. And then you want to predict also the links. Okay, so it's really everything of what we talk about is there. Node classification, link prediction, everything. Okay, you want to predict whether something is a claim or not, where these attacks there, or okay. So suppose that you have some data, okay, which is, better if I show you text. Argumentation mining, data. Okay, you have, for example, this is a data set of persuasive essays. These are essays written by high school students, okay? There is a title, should students be taught to compete or to cooperate? And here is the essay, okay? This is labeled with ground truth. This is, so the first column is the sentences, and the second is the class. Basically, C stays for claim, P for premise, M for major claim, and so on. So suppose that you would like, for example, to, let's take just one of the tasks in argumentation mining. You want to predict whether a sentence is of this class, one of these classes, okay? So the task is sentence classification. You have a list of sentences, and you know that they are of class N, M, C, or P, whatever they mean. So how can you model such a task? Sentence classification, you can think of it similarly to sentiment analysis, okay? You have sentences, and the class is positive, neutral, negative, okay? Is a sentence classification. Can you spend the last 5 minutes in thinking how you could model sentence classification? And then if any of you has some idea, I'll try to write the model in any of the languages that you, maybe just let's write the rules, the predicates and the rules. If you have an idea, please raise your hand. I'll give you, okay, a couple of minutes, 3 minutes, and then I will try to model it. If none of you has suggestions. If someone wants to try, what are the objects of our domain? Think about, I don't know, the types of objects. What do we have here? Words, exactly. Then sentences, perfect. Good, okay, so one way is that we write, you wanna try? You wanna try? No. Sentence classification. Say, so you have, he said, so one possibility is has word, like I did for web pages, okay? So a sentence has a word. Okay? So this is Markov logic, and this would be, let's try to be capital or lowercase, doesn't matter. Then you have classes. So you may say, for example, that the category of a sentence is a certain class. Okay? That's one possibility. But it's not the only one. You could say, for example, that suppose the classes are just claim and premise. You could say also this. Okay? You build two predicates for each class. Oh, and also you have maybe none. So in this case, this is your query predicate. And now, no matter what, if we are using MLN or Prolog like stuff, but this is the target. In this case, instead, you have 3 different targets. It's modeled differently. But with this, we do not have what? What is missing? If you look again at how an input document is, it's like this. This is the title, and these are the sentences of your essay. What are not considering here? Okay, that's a good point. Classes are mutually exclusive. Right, that's a good point. Then, correlation between sentences, okay? So, we need, for example, something that says, next of a sentence is another sentence, okay? So, consecutiveness. Or, as your colleague said, mutually exclusiveness, which now now we are moving to constraints. This is not in the modeling of the predicates, but is in the part of the rules. Okay, so for example, in Markov logic, you would write that it's not possible that sentence is a claim and premise at the same time. Okay. In Prolog-like languages, you would write that claim implies, for example, if it's not a claim, it's a premise. Sorry, if it's a premise, it's not a claim, and the other way around, you can write that. These kind of things. But this, again, we are moving to the rules, okay? So what other things are also missing is the semantic of the word, okay? And this is tricky because it's hard to encode something that comes from, for example, ontologies, dictionaries. You know that, for example, I firmly believe that. Okay, this is probably very likely to introduce a claim. I firmly believe that. But also, if you had said, I firmly argue that, or I firmly claim that, okay, claim, believe, and argue are three words that should mean something, okay? So they are synonyms in this sense. So you should put this information within the predicates, otherwise fridge is as similar to claim as believe is, okay? All the words are orthogonal, okay? So when all this is to say that this is true with any machine learning problem, the preprocessing part is really what makes the difference. If you have the best algorithms that you can imagine about learning about inference, but if you have input the wrong stuff, no way. So you have to build the model with a lot of carefulness. And in statistical relational learning, particularly in my experience, there is a lot of trial and error with trade-off between expressivity that you would really like to have. The first models that you write are expressive a lot, but the complexity then kills you soon. Okay, so this is the most difficult thing to achieve. And again, you should convince before the others yourselves that statistical relational AI is useful for the problem that you have. And it has something more with respect to propositional classifiers. Okay, so we are out of time. So sorry that I covered fewer examples than I would, but okay, that's it. Thanks. If CP has finished. Let's see that. Yes. And yeah, that's very interesting. Do not go away, because that is exactly what I wanted to show. That he said, thank you for remembering this. It has learned a very interesting clause, which I didn't realize was in the data that I prepared. So thanks a lot. This is very, very interesting. The query, okay, the query was apartment, rent, and Boston, okay, the query. But I built the data set, I didn't notice, in a way that the relevant pages are 1, 3, and 4, which contains rentals, are the only one that contain rentals. I didn't notice that when I built the data. Okay, that's, believe me, that's true. And so, Fabrizio, very good job, because it correctly predicted something that doesn't have to do anything with the query, but it had to predict this. So it really captured this rule. And sometimes structural learning surprises you because it notices something that you don't. Yeah. So it worked. Probe foil actually learns the same rule here.